Hello, it's Stat 134, Lecture 4. You have a quiz next Wednesday on Chapter 1. Last time we talked about independence, and I just want to make sure you realize that if A and B are independent, then A and B complement are independent, A complement B are independent, and so on. I actually provide you here with a little proof of that. For example, I show you that if A and B are independent, then A complement and B are independent. You can see here that I can write A complement as omega minus A. Omega is the entire outcome space. And so A complement B you can write as B minus AB, because B distributes into omega minus A. And so by the probability of a difference, we know that this is probability of B minus probability of AB, and then probability of AB by the multiplication rule for independent events factorizes, and you can just follow the rest. We also saw Bayes' rule, and I just want to mention that there's forward and backward conditional. So forward conditional is also called a likelihood. Backward conditional is called a posterior. You only need Bayes' rule for backwards conditional. So, for example, if you were to calculate the probability that you have die 1 given that you have a 6, this would be a backward conditional. You need to use Bayes' rule because the natural ordering from the tree is that you would have D1 and then you would have a 6. So today we're going to go over student responses from a concept test, and then we'll talk about independence of 3 or more events. We'll discuss the binomial distribution and consecutive odds ratio. So student responses to the concept test, you guys did great on this. Suppose A and B are 2 events with probability of A is 0.5 and probability of A union B is 0.8. Is it possible for A and B to be both mutually exclusive and independent? I just love this little hieroglyphic here. So, but that was wrong. Mike said it's B, so you know the answer is B. Good. But some other explanations here that are great. You can say that since A and B are independent, probability of A and B is probability of A times probability of B, which is not 0, and this contradicts the assumption that A and B are mutually exclusive. Or you can say, if you remember from class, that you can only get A and B to be ME and independent when A or B are impossible. So independence of 3 events. Let's first talk about what it means for A, B, and C to be pairwise independent. So pairwise independent means that for any pair of A, B, C, we have the product rule. We have the multiplication rule as given here. And so, for example, if you have 3 people, let Bij be the event that person I and J have the same birthday. So notice that B12, B13, and B23 are pairwise independent. So, for example, you need to show that probability of B12, B13 is equal to probability of B12, probability of B23, and you can just see that this is the case on the left-hand side. B12, B13 is to say that all 3 have the same birthday, which has probability 1 over 365 squared, and that's the same as on the right side. We say that A, B, C are independent if A, B, and C are pairwise independent, and the multiplication rule for A, B, and C is given as written here. And just like for independence of 2, if A and B are independent, then we saw before that you get A complement, B are independent, and all variations of complements. That's also true here. And I drew out a tree for you just to show you what it means to have probability A, B, C be equal to probability A, probability B, probability C. You can see, just if you look at the top branch here, that to have the multiplication rule, that we're going to need probability of C condition on A and B being true equal to the probability of C. And notice that that does not follow from pairwise independence. Pairwise independence does not give you this equation here because it involves all 3 letters. So that's one way to think and understand why independence is a stronger condition on A, B, and C than just pairwise independence. But let's take a look at an example to further illustrate this. So is B1, 2, B1, 3, and B2, 3 independent? So you would, we already know that they're pairwise independent from above. Is it independent? So you need to check that the multiplication rule holds, and you can see that it does not. So probability B1, 2, B1, 3, B1, B2, 3. So this event is just to say that all 3 have the same birthday, which we know is 1 over 365 squared, whereas on the right-hand side we have 1 over 365 cubed, so they're not equal. So just because you have pairwise independence doesn't mean you have independence. So then we moved on to the binomial distribution. So the binomial distribution is a most important distribution that we'll study. But we'll start baby steps, is the Bernoulli P trial. And a Bernoulli P trial is basically an experiment that has 2 outcomes, a success or a failure. It has a success with probability P and a failure with probability 1 minus P. So for example, you roll a die, you either get a 6 or you don't get a 6. So now a binomial NP distribution is when we have n independent Bernoulli P trials. So there are 2 parameters now. There's n, the number of independent Bernoulli trials that we have, and p, which is the probability of a success for each Bernoulli trial. And so this p is it's a fixed probability, same for every Bernoulli trial, and this is an unconditional probability. So for example, we roll a die n times. What are the possible number of successes, you may ask? So the chance of having each of these numbers of successes is called a binomial or bin NP distribution. And those probabilities are given by what's called the binomial formula. So here k is the number of successes. So this is a number between 0 and n. And n is the number of trials. P is the chance of success. And so, for example, you roll a die 5 times. What's the chance of getting 2 6s? So here n is 5, k is 2, and p is 1 and I've shown the histogram on the right here. So you can actually compute this. So the probability of having 2 6s, according to the binomial formula, is given by the equation here. So it's 10 times 1 6 squared, 5 6 cubed. To understand this formula better, let's think about all the ways that we could get 2 successes, right? So success I'm just going to write as 1, failure 0, like in computer science. So the chance of getting 1 1 0 0 0 is 1 6 squared, 5 6 cubed, which is the same for like if you have it in a different order, 0 1 1 0 0. How many of these are there? Well, there are 5 different positions for the first one. So the first one could be in any 5 positions. The second one could be in any of the remaining 4 positions. The first 0 could be in any of the remaining 3 positions. The second 0 could be in any of the remaining 2 positions, and then the last 0 is fixed. So that gives us 5 factorial different sort of permutations of 1 1 0 0 0, but the 2 1s are indistinguishable and the 0s are indistinguishable, so we have to divide by 2 factorial, 3 factorial, and that is 10. We can write 5 factorial, 2 factorial, 3 factorial is 5 choose 2, or 5 choose 3, or 5 choose 2 3. So then we did a concept test. So 10 cards are dealt off the top of a well-shuffled deck. The binomial formula doesn't apply to find the chance of getting exactly 3 diamonds because A, the probability of a trial being successful changes, B, the trials aren't independent, C, there isn't a fixed number of trials, D, more than one of the above. So many of you said more than one of the above, but the truth of the matter is that the probability of a trial being successful always is the same. So the key here is that that the P, the probability of having a diamond, isn't, so that's an unconditional probability. So the unconditional probability of having a diamond for the first trial, second trial, third trial, fourth trial are all the same. It's 1/4. So of course, if I condition if I condition on what happens before or after, then that would be something else, then it would change, but I'm not conditioning. So just remember that the probability, when we say probability is always the same for all the trials, we mean the unconditional probability. And so you might ask yourself, how could you have like a different probability? How could the probability change for the trials if it's an unconditional probability? Well, I guess you need to be drawing from like 2 different decks, one with like 13 diamonds and one with like 20 diamonds or something like that. So there would be, depending on which deck you're drawing from, you would have a different probability of success. But that's not the case here. Here we just have a single deck. The trials aren't independent because we're not dealing the cards with replacement. And of course there is a fixed number of trials, that is 10. There was a second question here. Here we had our box consisted of 9 zeros and 1 1, so the probability of a success was 1/10. N was 5. We're drawing with replacement, so we have independent trials. And K is 3. The sum of the draws is just the number of successes. So yes, this is a binomial formula is applicable. Consecutive odd ratio is a tool to find the mode of the binomial distribution. Now the mode is the K such that the probability of K is largest. So here, for example, is the binomial distribution for n is 5, k